right. Good afternoon, class. Happy Tuesday. Hopefully you had a nice weekend. So I was able to get the midterms graded over the weekend. I guess the average was around 81% or so. So I guess sort of based on that, it didn't go too bad, which I guess that's sort of good news. Hopefully, the exam didn't really throw you off too much. It was relatively based on the homework problems, as I said it would be. I had maybe just like one or two questions towards the end where you had to do some sort of, how shall we say this, response type questions. So that might have been a little bit challenging-ish, but hopefully the exam wasn't too bad. Maybe that recurrence relation one might have been a little bit challenging. I guess those are always going to be a little bit sort of going to be always tough, the recurrences, I guess. I think the first one, the recurrences gave the most issues. So before I begin anything today, I'm going to go over the exam results. I'll go over the solutions on them, and then I'll sort of go over Zoom from last week's lecture. Let's go ahead and start a screen share. Let's begin. Okay, so this was basically our first question right there on the midterm. So ideally, these ones are a little bit, can be a little bit challenging to work out, but obviously 2 to the 64 is a constant, so even if it's a big constant, it is a constant that's not growing, so we can set that as our smallest one. Now, I guess I'll sort of go over all the groupings over here next. So basically here, these two both have the same n root n growth rates. Remember, n root n is going to be bigger than n log n. Now, log squared of n is log n times log n, which is going to be less than n log n. So obviously, this has to be bigger than n squared, than log n squared. And if we take the square root of n cubed, it's going to be also, it's going to be n 3/2, which is n root n, which is bigger than n log n using L'Hopital's rule. So these two have the same growth rate. They're both n root n. Now, this one from lectures I've covered, so 2 up to the log 2 of n is going to be n. That's just one of our sort of identities for logarithms. And then this one, we can rewrite this part a little bit to get actually, so we can convert the base of logs from log 4 to log 2. So we get log 2n divided by log 2 of 4, I believe. So we end up getting 2 up to log 2n over 2. So it's going to be essentially n up to the 1/2, so it's going to be root of n, which is going to be less than this one, which is linear. And these are both going to be less than n times root of n. So these two are both going to be less than these ones right there. These ones are equal because they're both n root n. These two are both going to be quadratic, which are both going to be larger. They're both equal, but they're both larger than n root n. And the biggest one, obviously, is our exponential growth rate. So that was question 1. The only tricky part really might have been just maybe this one. I've been the only one that might have thrown you off a little bit. I would imagine the rest, I think, isn't too bad. So first I went over how n root n is bigger than n log n. And log squared is log times log, which is, if you interpret it as n up to, if you interpret this as actually as this, let's say by accident, well, it wouldn't have made a difference. It's still, n root n is still bigger than that too. So wouldn't have been any difference if you had misinterpreted that. So I think this one did cause some issue with students for question 2a. I guess solving recurrences is always going to be sort of challenging to do. So I allowed you to also use master theorem. So for this one, I guess the answer was you're supposed to have worked it out the way we do it in class. And then also, as well as if the problem can be, if you can apply the master theorem on some of these problems, then apply the master theorem as well. So this one, we end up getting this type of expansion of our recurrences. And then we have to sort of factor this 4 back in at this point. I kind of kept the root n's sort of separated because we can see a definite pattern here. We have root n, then 2 root n, then 4 root n. So we have this the following pattern we end up getting. It's right there, which is, you can see that. Okay, well, yes, that's sort of it's kind of way it is, I suppose. So yeah. So in this case, we end up getting this summation right here, which using our sort of 2 to the power, so 2 to the power I, that ends up being essentially the following summation we get. It's going to be 2 up to the log 4 of n plus 1 minus 1. Remember, in this case, I won't be n. I is log base 4 of n because we can substitute n to be 4 to the power I. So then, same idea, 2 to the power log 4 of n, that's just root of n. So we do a little bit of algebra here. We end up getting essentially n. And master theorem also gives us n as well because it's going to be case 1 for the master theorem on this one. So we get O of n because it's O of n because we're using this inequality where T of n is less than or equal to that right-hand side expression. So it's going to be big O is used in this one. For question B, we use equals, so it's going to imply theta. Now, I use a recurrence tree on this, but I kind of didn't show it here. But every level is going to essentially be 19 over 20 to the power I. So the first level is obviously 0. Next level was 19 over 20n. The level afterwards was 19 over 20 squared. And so every level gave us this kind of pattern. And we have actually log of 4/3 n was our base of our log, but it doesn't really matter because since the exponent in that summation is less than 1, it will converge to a value. This will converge to 20, I believe, using the summation rule for series where 1 is less, so where the exponent, sorry, where the base is less than 1, so it gives us actually n. So it's going to be theta of n because for question B, I believe I had T of n equaled that sort of recurrence relation. And then for part C, it was, we used the, what's it called, the antiderivative method. So we had T of n equal T n minus log of n plus equal log squared of n. So we set it up in this type of form, and our delta n or delta x was going to be natural log. So we divide natural log to both sides. So now our derivative is natural log. So T of n is just antiderivative of this, which is just n log n minus n, which is n log n. We use omega because this is where it was T of n was greater than or equal to that right-hand side expression. Also, if you look at the exam midterm sort of your submission area, I did actually upload a PDF with my annotated notes. At least it should show that. So I used sort of drew on the PDF using my writing pad, and it should have all the sort of the comments and grades and what you lost points on and so forth with your midterm. So anyway, that was question C. So this one, question 3, caused some issues. So this was how you wanted to work this one out. So we have A and B. Use that Karatsuba's method. So we have A11, A12, and then B11, B12, and we apply that formula. So that first and second box, it involved a recursive function called, and for a third one. Now, I computed these results at the end, right here, and sort of underline this. I simply just use these at the very end. But anyway, to compute these, you have to go ahead and keep on working at the recursively process those. So this was for the first recursive function, applying the same trick except that we have these size 1 numbers. Now over here, this multiplication resulted in a 1-digit by a 2-digit number, which this could be done sort of, I guess you can do it relatively in constant time. You don't have to really do any recursion there. We can just sort of just compute that right there on the fly. The rest of these numbers are all just could be done very quickly. So this would not cause any issues at all. And then we just sort of combine them, we get this number. Turn that up over here, and we can use that in this subtraction part for that topmost function call. We go ahead and work out part 2. Right there. So same idea, we just sort of separate these numbers, and this could be done also relatively fast. You don't need any recursion there for that, but each one of these can be done pretty quick. We just simply apply these at the end like that. And then we end up getting, if we do some basic arithmetic, we end up getting this number here. It's the green box at the very bottom. And go ahead and I sort of plug this in over here. I also can use it here as well. And we have to go ahead and work out for question 3, or for part 3, we have to work out this recurrence as well, or this recursive function call for this instance. And I guess one thing I might have caught some people was here we end up having, let's see, so it was so using Karatuba's method, we actually, so that formula we're given, this one was actually, we went ahead and let me just see. Just try to double check this here. So I have to look at the formula for this. Let me just take a look. I haven't memorized the formula actually, but that was using the formula given. So let's go ahead and just see if I can pull this up really quickly. So the final term was actually, I think I had to rewrite this. But it's the right answer, but maybe I didn't rewrite this part. But it's A1 plus A12. It's going to be actually A11 plus A12. Oh, I double check my work here on this one. So we have basically, we add up these two together. Oh, again, now I get it. So I took 24 plus 75, and I'm getting 99. 64 plus 21 to get 85, and we multiply those two together using that formula for this Karatuba's method. So just the directly using a formula, that's sort of that I gave you guys, which you could have used, I guess, during the exam, because I can't really verify who's using notes and so forth. So I guess I did say it wasn't beyond there, so of course you could use those notes, but we just simply take 24 plus 75 multiplied by 64 plus 21. That's our final term right there. That's how we end up getting that. And then this will imply another recursive function call right here. And as you work this one out, this basically we have to do a recursive call right there, because this is going to be two-digit numbers, which will cause a fourth function call. Very bottom. Then we go ahead and just combine these all together. Combine this up here. Get this result. Return that up. Then we have to simply reuse 1 and 2 at the very end, and we just do all those additions, subtractions at the very end, and we end up getting this result at the very end. So if let's say your numbers would have came out a little bit wrong, I probably don't think I would have taken off points for, as long as you kind of got each recursive sort of call. If you're able to get these, that was really the only, it's kind of a stickler for, I guess, was just making sure you got those 4 function calls basically. Got those, and that was pretty much the that question. So, and only one that might have caught some people might have been just this one for part 4 might have caught some people, but then it wasn't a big penalty for that though, just a few points off for that, so it wasn't too bad. So, on to the next question here. So for question 4, got the exact sort of set of numbers. It's not written here on this OneNote, but that's okay though. So this one, basically, we found the biggest number in our set, which was 672. It was 3 digits. So we divide every number by 10 to the power 3, or by 1,000 to each of these numbers. Multiply it by 8 to map it to a position in this into this sort of array of linked lists. So these numbers right here, all of these, right, if I took each of these and divided by 1,000, multiplied by 8, they all had some type of a 0 point something. So they all had the value 0. Then for 314, this number, if I divided by 1,000 multiplied by 8, I think it gave me around 2.4 or so, which would be just 2. And then same thing for 555 and 672, divided by 1,000 multiplied by 8, it gave me 4 point something and 5 point something, which I put them into those 2 spots. Then sort this topmost bucket, and then sort your list. For the most part, there was not many issues with the bucket sort problem, so it wasn't too many issues with this one. Radix sort, this one didn't have too many problems, but I think some people kind of sort of shortcut this way too much, where they ended up just sort of showing me only these three arrays, and that was it. And I was saying, well, I mean, wasn't like a zero for that, but it's like, well, how do you get those? It kind of seems like magic how you got them. So you had to have shown some kind of work. It did take a little bit of work to do this, but I guess the trade-off was it gave you more time on the exam. It wasn't a hard exam, so more work versus a hard exam, I think, is more favorable. So it wasn't really a tough question, really. We first sort them by the rightmost digits using, so these two arrays, this is going to be our C array for counting sort. First, we had to sort of set up the number of counts, how many zeros we see, how many digit fours we see for the rightmost digit, we count those up. Then we have this, and we go ahead and modify that same array to create this array, which will tell us where we're going to insert every element into our final array at the end. Using the same radix sort we've been doing in class. I went over the example back then, and also for homework. Nothing really different here. It was just same problems, different set of elements, but same questions. So it's your first pass, second pass. So we sorted now by that second digit, and then our last pass we sorted them by our leftmost digit. We end up getting this. So that was basically all there was to radix sort. So of course, look the answer over if you want, but I won't go over it here because there's not really too much to it other than this, really. So just using the same method for radix sort that we've covered already in this class. And for question 6, so if you used insertion sort instead for every iteration, for every pass, a radix sort, it would work because insertion sort is a stable sorting algorithm, and it would be n squared time because you would sort of run this insertion sort and sort of d number of times, and d will be always a constant, or it will be usually a constant. So we do d times n squared, which is n squared. So the n squared runtime if you used if you used insertion sort instead. Question 7. I multiply this matrix by itself. Typically, the straightforward approach would involve doing 8 multiplications, but here we can sort of modify this a little bit. I'm going to zoom out so we can see all of this. So essentially, whatever I have there in red and blue, we can sort of factor out so that A1 times A2 plus A2 times A4, we can factor the A2 out like this. We can factor it out, which will now involve, oops, supposed to be addition right there. Let's be an addition. So we can add those two up, which will not involve multiplying. Then we multiply A2 to that whole sum. So we take that 2 multiplications and we make 1 multiplication out of it. And same idea for this other term. We can substitute this to create this sort of result, which is going to be the same result, but we only have 1 multiplication. And then that part there in green, that green box, well, that's a repeated term. So we can simply reuse the earlier one, use that again, so you don't have to multiply this twice. You have to do 1 multiplication for that. So if we see this, we essentially have 1 multiplication. So you have 1, 2, 3, 4, and 5. Is going to be our number of multiplications we have here. So it just involves doing a little bit of factoring some numbers out and reusing old results. So wasn't too many issues with this question either. So I think the most part, the issues were with the recurrence relations. That one had several problems. The reordering functions from smallest to highest growth rate had some problems. Maybe some of the Karatsuba's algorithm for multiplying 2 big numbers was some issue, but I think this one had not many problems for 7 or 6 or for 5 or 4, had not many problems either. So exam was 82, 81% was the average. So I don't have the complete stats of deviation and so forth, but I guess it was a pretty good average. So I'm guessing it was okay. It's not a bad exam result. So the final exam will be similar format to this. So I think having a take-home kind of exam like this, you sort of work it out and upload it, scan it. I think that ended up being pretty good. I didn't see any real issues with that. So the final exam will be a little longer, obviously. It'll be 2 hours long, but the content won't be more. So it's going to be just really non-comprehensive. It'll cover content after this midterm. So just, I guess, make the exam a little bit nicer. So it'll be really the same amount of work. It won't be actually a bigger exam. You'll have more time to work on it. So I guess, you know, and of course, if you have any issues uploading, it would let me know. I can give you more time to give you time to upload as well. So you don't have to worry about not uploading it. I don't want to have you rush the upload and then you upload the wrong page or something because of that. So I always try to give you time on that if needed. So anyway, that's that. I guess I could also convert this into a PDF, upload this as well, solutions to the exam. So that way you have them as if we look them over. And of course, let me know if I made a mistake grading them. Let me know if if I didn't add up your points correctly. So it was out of 90 points. What was your total? So that was that. So that's going to be the midterm results. So I guess now we can go back and continue from last time's content, which was we were going over binomial heaps last week. So let's go ahead and go to the one note here. Let's see, where is it? Binomial heaps. So I'll just recap this kind of quickly. So the idea of binomial heaps is really just to refresh this. We essentially have a priority queue structure where we're going to use a min heap for our examples. So it means the parent has a smaller value than all of its children. And the idea is we have several binomial trees that we connect together. So you have a forest of binomial trees, essentially. So what happens is we use the amount of elements we have in our structure. We use a binary number representation so we know what type of binomial tree we have in this particular instance of our binomial heap. And then for insertion, all we ever do is we just create a new binomial tree, a B0 tree, and simply merge it into our binomial heap. That's really the pattern. So for our first example, we merge a B0 tree, and we got this result. We insert 5, we just merge a B0 tree again, merge it into our current structure, so we have already a B0 tree, so we have to merge these to create a B1 tree. So you can't have duplicates of a binomial tree. So if we have two B0 trees, we merge them into a B1 tree we had over here. Then we have this B1 tree, we insert 2, we simply have to just merge a B0 tree. And this green line here is just sort of connecting our forest. So we have a B1 tree and a B0 tree, and that's going to be in our forest, basically. Then when I go ahead and insert 7, we're going to insert a B0 tree, so you have to merge this 2 and 7 to create a new binomial tree. So you have two B1 trees, you have to sort of merge them to create one B2 tree, and so on. Insert 6, create that. We insert 10, we have to merge it into our 6 tree. Then we insert 1, then we insert 0, which will cause a lot of merges because the 0, the B0 tree merged to our other B0 tree. Then we have these two B1 trees. We merge them into a B2 tree, and then we have our two B2 tree to create one B3 tree. So we have to do all these merges basically at the end. So then the insertion runtime, well, the idea was we had to do a lot of possible merges in the worst case. So in the worst case, we have to do log n merges. So every tree is going to get merged. And for every instance of a binomial heap, we'll always have no more than log n number of trees. So we do at most log n merges in the worst possible case. But the worst case does not always happen for binomial heaps. So for that reason, we can actually amortize the cost. So a lot of times we do insertions, it will actually take constant time, but then there's that one instance where it will take a lot of time. You have to do a lot of possible merges, but it happens only once every now and then. So we can easily amortize it to be roughly constant. If you average out all the insertions together, it'll be roughly constant for every insertion, which is an improvement. to a binary heap, which every insertion, if you amortize the insertions for a binary heap, it would be log of n. Binomial heap, if you amortize them, it will be better. So that's going to be the insertion. So now you want to go ahead and do deletion, which is the next sort of topic for binomial heaps. So I'm going to now, I guess I'll draw a line over here. So go over deletions, next sort of thing. So basically, I guess for any kind of priority queue structure, we want to always know how to insert and delete. That's the two main sort of operations for any priority queue structure. So basically, what's going to happen is we're going to have to first find a node, find the root node in our forest. With the smallest value, smallest key item, whatever you want to call it. So typically we can have a pointer that always points to it just to make it faster, but we can of course, traverse to all of our head nodes and find the smallest one, but we typically always maintain some pointer pointing to that smallest element. And then we're going to basically sort of remove that node. That node from that binomial tree. Not a very scientific term, but from that, so from our binomial tree, whose root element was the smallest among all of the other roots, from that binomial tree, remove that node, that head node. And then removing from binomial tree is going to so the result will be a set of binomial trees B0, 1 to bk minus 1. So for that particular, let's say if that tree was a B2 tree, then it would create a B0 and a B1. If it's a B3 tree, it's going to create B0, B1, B2 trees will be the result. If you disconnect, if the root gets removed, then you're going to create all these subtrees will be the result. And you have to basically merge all these subtrees. Then merge. I put this below one level because it's kind of, so merge. Those subtrees. And that's really all deletion is all about. So it seems to be a little bit easier, actually, maybe a little bit easier than doing deletion from a binary heap. So let's go ahead and just now go ahead and do some examples of this. I have my notes over here. I'm going to go ahead and just have a brand new binomial heap structure. Let's go ahead and just sort of use the one I've written. I'm going to have one sort of pre-created. Let's do a few examples of this. So I'm going to have, let's say we have 3, 12, 7, 13, 15. We'll have 2, 5, 11, and 19. We'll have 21, 30. We'll just have 1 by itself. Go ahead and put the circles around these as well, so it looks better. Our current is going to be our initial. So let's say we inserted a bunch of elements into the structure. So we have the following binomial tree that are following forest over here. And just it's in there, and then we're going to go ahead and link them together. I'll use sort of a green arrow, green line to sort of connect these. So green line implies that is going to be a set of binomial trees, and this green line is going to just sort of connect them. So we're going to have a forest of all of these sort of trees, and then our we're going to have the following. We're going to have sort of a B0 tree, B1 tree, B2, and a B3 tree we're going to have. So now we have this. Okay, let's go ahead and just sort of run this delete min operation on this particular instance. This will be a very simple example. Oops, okay, spelled wrong. Delete min. So of course we can go ahead and find which root of these trees has the smallest element, but of course we can always maintain a pointer that always points to that smallest element, so you can just right away, instead of having to look for, we already have a pointer pointing to it. So for this example, it's very simple, delete min. All we have to do is basically just remove this from our tree. And then find a smaller min. So you have to go ahead and start from the leftmost position and then traverse until you find our min. So here we would go ahead and sort of set 3 and 2 compared to 21. So then 2 is our new min. So you have to sort of go ahead and do that. So this will take a log n number of steps because we first delete 1, then we have to go ahead and find our next smallest. So that will take log of n steps. Now, you saw here, essentially did a linear search. So that the standard 135 method of finding the smallest element in the list. The thing is, we're only looking through the root of each of these trees. And there'll be no more than really log n number of roots. So this loop traverse will take log n steps. So it's kind of nice about this. And of course, we can remove sort of, in this case, we're going to have the following result. We had to remove one of our we had to remove one of our B trees, or 0 tree, because that was where the smallest element happened to be. So the result now is going to be just 1, 1, 1, 0. We have 0 trees, 1 B1 tree, 1 B2, and 1 B3. Let me go ahead and actually just copy this. I'll have to redraw this entire picture. Put this below. Set to do that. Go ahead and do a little cleanup here. So this. Now we're going to have a pointer pointing to that node right there, which will be our smallest element in our structure. And we have the following binary representation of this. So we have sort of 0B, 0 trees, 1B1, 1B2, and 1B3. Okay, so now, once again, I want to go ahead and do a delete min, just like before. So let me make sure I'm consistent. So, okay, delete min. This again. And this time around, we're going to remove from our B1 tree. We're going to remove from this time because in this case, our smallest element happens to be in our B1 tree. So what happens now is we're going to take this 2 and sort of remove it from this tree. So the result now is we're going to have these 2 trees. Let's try to do this too. So this was a this was basically a B2 tree, right? So we're going to have basically our B0 tree and our B1 tree are the results. So we remove a B2 tree, which is this entire tree right there with a B2, and we're going to now have to take our two new trees, B0 and B1, and merge them. So right now, in this structure, we're going to now remove, so we're going to subtract 1 from this. Actually, not 1, but 1, 0, 1, because we're removing a B1 tree. Sorry, no, say this. A B2 tree was removed, basically. So our result for right now is going to be 1, 0, 1, 0. But then we're going to have to combine a B0 tree, which is not going to cause any real problems because we can just go ahead and just combine that to get 1, 0, 1, 1, which is just fine. And then plus we're going to have to merge a B1 tree. And that's going to cause some merging to have to happen. The result is going to be 1, 1, 0, 1. So we have the math. Let's go ahead and actually draw this up. So this 11 by itself is not going to cause any issue. We're going to have to merge the 519 with 2130 because we have these two B1 trees. We have to merge them together to create a new structure. So I'm going to go ahead. I'm going to actually try to copy. I'm going to copy this tree. It's a bigger one. Copy this one right here. Just that one. Hopefully it's copied. Put this down below so I don't have to keep redrawing that. So we have this result. So 11 will be by itself, and then the 519, 2 and 30 will be merged. So 5 will be the smaller, as a smaller element than 21. So 5 will be the root of that tree. We're going to have 5, 19, then we're going to have 21 and 30. We're going to merge into its own. 11 will be just sort of by itself. It's a B0 tree, there's nothing to merge with there. I'll sort of move this over a little so it's not so sticking out there. 11 will be by itself, like that. So I'll go ahead and just sort of circle these so it looks consistent with the rest of our pictures. Then we're going to now connect these elements in our. We're going to have a forest of these binomial trees. And now our new smallest element now is going to be 3. It's our new root element. So the result is going to be this tree. So we're going to have, let me just make sure I get this correct, 1, 1, 0, 1, 1, 1, 0, 1. We have a B3, a B2, and a B0 tree. There's no B1 tree in this picture. That's a result of after deleting our min element. So you have to do all that work. You have to sort of split up that tree and then merge them. And you have to go ahead and traverse and find our next smallest element. So you have to loop, iterate through all these. So essentially, each of these roots will have a pointer that will connect to each other, and it'll be a doubly linked list in a sense. We can kind of, traverse through each of these and find our smallest one and have some pointer point to the smallest root element. So this will be, you're going to link these all together in one linked list, the roots, and then each root will link to its children like that. So it's a giant sort of crazy linked list structure, but there's ways to make it a bit more organized, but over that later on. So anyway, it's going to be the result of doing a delete min. Let's go ahead and do another delete min. It's going to be a lot more chaotic this time because now our smallest element, 3, happens to be our biggest binomial tree in our forest. Let's go ahead now and just do a delete once again. Delete min. So obviously 3 is our smallest element, so we're going to have to remove this from our structure. It's a B3 tree, so we're going to have a B0 tree. We have our B1 tree. And we're going to have our B2 tree. Let's wait a second. This. There's our B0, 1, and our B2 trees. So we remove, this is a B3 tree. If we remove the root, we create these new trees. So we have B0, B1 to B2. It's a very elegant structure, actually. I'm still amazed at how nice this actually, whoever thought about this, really very elegant structure, actually. So anyway, now we have these. So basically, we're going to have to go ahead and merge them into our current structure. So we're going to first have to merge a B0 tree to what we have. So first, we're going to remove this tree. We're going to move that B3 tree gets removed first. Give us that. Then we're going to merge our B0 tree, which is going to cause merge to happen. So we're going to add this and we have to merge. We already have a B0 tree currently already in our forest. So we're going to have to merge that. And plus, we're going to have to merge our B1 tree. Sorry. Create the following. We're going to have 0, 1. And then it's going to cause, this is going to merge these together, sorry, which will cause these to also merge. Like that. So what happens is we had this B1 tree merged into our existing B1 tree, which is going to cause that to merge to our existing B2 tree, which is going to be right here. So this will be interesting. And at the very end, we're going to have to merge our B2 tree. I hope I did this correctly. Our B2 tree at the very end, merge. Let's see here. I think this came out correct. Let's double check my notes to make sure I didn't mess this up. Could be an issue. I'm gonna go ahead and sort of draw this out and see what happens. So I just see if I can visualize. I think I might have made a mistake here. Let's just see first. The first thing we'll do is we're going to merge this 7 with our existing B0 tree. So we're going to first merge these two together. So 7 will be the root of this. So we have 7 and 11 merged together. Let me just first do this kind of step by step. This might be a little bit, it gets a little, get a little thrown off as well right here. It's a little bit easy right now. So let's first do that. We merge these two together. And then this creates a B1 tree. We have to merge that with our 9 and 10 tree. That's another B1 tree. Okay, so then this B1 tree, 9 and 10, will merge with this. So it's going to, 7 is going to be the root of that. So we have 9, I think it's 9 and 10, I believe. Let me just double check to make sure I'm correct, 9 and 10. Try to draw a little bit more to scale. And 10. Now we have two B1 trees like that. So we merge these two together like that. And now we actually have actually a couple of, we have this, we have two B2 trees. So we'll merge this with our existing one first, since we're still on the process of merging this. We'll merge with this B2 tree, because we have this B2 tree over here, plus that. So I'm going to first just do a step by step. So I'm going to first have this created. We first have to merge 7 with 11. Just go ahead and do like this first. I'll probably do it step by step actually instead, just so it's not so crazy. So let's go ahead and do this first. So I'm going to first have 7, 11. I'll have 9 and 10. I think this is better if I just do kind of step by step. Righty. And then we have these will be sort of linked together currently. And then we're going to have to merge these. So we're going to end up getting, I'll just go ahead and I'll sort of redraw this, I'll sort of copy this. We're going to merge them now to create this structure. It's just going to be this. And now we have our existing, we have this tree here. So I'm going to go ahead and try to copy this. I'm going to redraw it. That. So we have that B1, or yeah, this B2 tree, sorry, right over here. And these would sort of have to get merged now because what happens is that really kind of a little bit weird looking. So I think I might have drew this one weird, I guess. But anyway, so now we have this structure set up. So you have to merge these two together, and then 5 will be the root of this new structure. So we have 5, let's say I have 5, 19. Let's see here. Let's try to make sure I get this correct. So this is kind of, I'm getting thrown off right here on this one. 7 and 5 is going to be the root now. We have 5, 19, 7, and 9 as a result. Then we're going to have 519, and then how am I getting right here on this one? So we have these two. Oh, I think I see why. It's going to be just 5, and we connect here 7, 9 over here. Okay, I got this. So 7, 11, 9, 10. Then we have 5, 19, 21, 30, and then we're going to connect these together. Okay, perfect. So that's how that would look. So now we're going to have the following here. So you have this tree over here. As our result. That. Then we have this B2 tree over here. This 12, 13, 20, and 15. Go ahead and I'll copy this. I'll copy that one as well so we can kind of, hopefully it's better for notes so it's kind of more step by step. We have this one. This over here. So I'll rewrite the one over here. So we have 12, 13, 20, 15. It's not going to cause that to happen because this is going to be a B3 tree. So we don't have to merge that. So then we have this at the end, B2, and a B0. Okay, so I think I made some math mistake over here, so I'll double check that later. But we'll have this tree at the end. Then we have our last two trees. Okay, so I think that was the right. So I don't know what happened there. So I'll like just redo that math part at the end. But anyway, now we have this. Then we have our B1 tree, 12, 13, 20, 15. Just keep them back and forth for a little bit. 13, 20, 15, 13, 20. Then we have 11. Like that. So we're going to go ahead and sort of connect these out. That's the result of that. So this caused a little bit of chaos right here, which as we already kind of saw. And connect these. That's the result actually. So I think I made a mistake with my additions over there somewhere. So I'll double check that in a little bit. I don't want to spend too much time sort of puzzling on that. But we end up having essentially a B3 tree. We have this. Actually, no, we have this. That's what we have actually. So I think I made a mistake with my additions above, but this is the right situation we have because we have to do a bunch of merges. So let me just go ahead and sort of recap what I did. I was kind of struggling here for a second, but the idea was we ripped out this 3. We had these trees over there. So the 7 had to merge with the 11. Then we merged that 7 and 11 with this tree, create that tree, and then we just had to sort of basically just, oh wait, where did 11 come from? Why did I mistake here again? Oh, jeez. Yeah, I think that was the right idea then. It was just these two then. Oops, I might have made a mistake then. But I'm missing something. Oh wait, that's because that's not supposed to be. Yeah, it is 11 over there. Okay, I don't know what's going on right now in my head. I think I'm missing. I think I might have done something weird. Ooh, this is kind of embarrassing. Let's see what I did here. So the 7 and 11 merged together. Merged 9 and 10. They merged out with these ones like that. So let me just try to see if I can do this really quickly here. So I first had to merge the 7 with the 11. Like that. Then we had to merge that with the 9 and 10, create that. Then we had to merge that with this one, create that giant tree. And then we just simply merged this B2 at the very end. I guess I was correct then. I think my math was actually valid then. That was my correct math. I guess I just must have made a mistake in my notes actually then. I kind of corrected right here. But this would be the final correct product. So I'll double check this later on, but it looks like to me this is correct. And of course, the 5 would be the smallest element in this binomial tree. So my notes had a mistake then, I suppose, but that's, I guess, there. So I'll double check this to make sure I didn't make a mistake here. I'll modify my notes if I need to. But anyway, that is the idea, though. So you have to keep on merging all these trees together that had the same number of nodes. That was the whole idea. So to recap this, B0 with this B0, then these two together would merge with 9 to 10, which would merge with this one. And at the very end, we just sort of combine this final tree together just like that. So that would be the result. I guess my math here was actually correct. I think my notes where I made a mistake on, which is, I guess, better than as I caught the mistake here. So that's pretty much a few examples on deletions. Let me see, should I cover another example? I could do one more example. So my notes are kind of now they're invalid because it's not even, my notes aren't even good anymore. I think I know why I messed up. I think my last time's example, I didn't draw the trees consistently. So it's always supposed to be, left side's supposed to be a larger tree. So I think on these ones here, I kind of messed these up as well. So I think I'll probably just not do any more deletions for right now. I'll have to redraw these trees because I kind of want it where the left side is bigger than the right side. So I think last time, I guess I might have made a mistake drawing these. That isn't an example above. Yeah, I don't want to really go too much into it. So I made a mistake on one of these right here. It's supposed to have it like, this is supposed to be on the left, not on the right like that. So that's okay. It's all right. I'll modify my notes, I guess, then we can go from there. So anyway, that's basically how a deletion works. So I guess I kind of butchered it a little bit here, but I will modify my notes before I upload these today. So let's go ahead now and just sort of go over the analysis of our deletions. So really, not too much, it's not really, the actual runtime is not so bad for this. So let's go over deletion runtime. So basically, each deletion is going to have to remove a node from our structure. So what's going to happen is that it's going to basically create at most log n number of subtrees, or roughly log n. So let's say we have this one big mega tree, then it's going to create about roughly log n minus 1 number of subtrees. So in worst case, removing a node creates log 2n minus 1 subtrees if you have a very big binomial tree that we're actually working with. And then each of those merges would be very fast because there wouldn't be too many trees to merge with. So essentially, that would be the worst case, and we have to merge all of them one by one, but each of those merges will take constant time, but there'll be log n of those trees. And then also another worst case scenario is we have to perform a merge operation O of log n time. So in some instances, we're going to have to keep merging other trees together and cause all kinds of mayhem, which I'll have to go through my notes. I think I have to be consistent with my binomial tree. That's part of my mistake that I made, which is why I got thrown off here and there. But the idea is that what's going to happen is we have to do at most log n combinations. After we break the tree apart, we have to merge all of them with existing trees, which will cause more merges to keep on happening, which is that big example, that chaotic example we had earlier causes that problem. So that means in the worst case, we're going to have to do log n number of steps. So it's going to be runtime will take O of log n. And we can't really amortize that. The amortization will still roughly be around log of n because this sort of scenario is very common to happen. We have a big tree, which is going to cause us to have to do a bunch of merges. So you could get lucky and always have our B0 tree always have our smallest element, but we can't really count on that. So the worst case, the smallest element will be in our biggest possible tree, which will cause us to create several log n minus 1 trees, which will all get merged to our existing trees in our structure. So this log of n time is going to be the typical case for deletion. So I guess deletion time is still going to be log of n, which is the same runtime it takes to do a deletion for a binary heap. But at least for insertion part, it's a little bit better. We can amortize the insertion part. So I guess the real benefit of a binomial heap is for insertion, because we can amortize that. So if we do a lot of insertions, not many deletions, then we can get a better scenario. So it depends on the situation that we're trying to work with. Now, the next thing I want to cover, just very briefly, I'm going to go ahead and talk about a Fibonacci heap just a little bit. I'm not going to really go too much into detail with this. So what this is going to essentially be just a lazy binomial heap. So it's kind of interesting that laziness actually sort of has some reward for data structures. So even for binomial binomial heap, it's also a little bit lazier than a regular binary heap, because not every insertion requires too much work. We have to do a lot of work on some instances, but if you sort of average them out, it's going to be pretty fast. Now, for a Fibonacci heap, it's even more lazy than binomial heap. So each insertion we just add B0 tree into forest, and then we do not perform merges. So there could be several B0 trees actually in a Fibonacci heap. So every insertion would just be, we just insert it, don't even worry about doing any merge. Just stick it into our forest, and that's it. Pretty complicated structure because of this, but we just do essentially this. We just insert it, and that's it. And then we have to do a deletion. Deletion occurs. Then we merge trees. So on a deletion, we have to do all that merging. But the thing is that we only have to do it only on deletions. So it's, if we do a lot of insertions, not many deletions, then we even have a better runtime than a binomial heap, or better expected. Maybe not asymptotically, but it'll be a little bit better, I think. Or not, I think, but it's going to be better than a binomial heap. But it's not really so common, because sometimes, that deletion could be a very large amount of steps, which could become a problem, but it depends on the situation again. So I'm not going to really spend time on Fibonacci heaps, but I guess it's just really just a lazy binomial heap. So we really just insert, will be no merging going on, but we merge when we have to do a deletion. So it's going to have a big hit right there. At least the insertions don't take too much of a hit, basically. So I'll have to go ahead and go through these and sort of redraw these trees a little bit more nicer for binomial things, a little bit inconsistencies here. but I'll draw that up later and I'll upload the notes onto Canvas. So this is basically the talk on binomial heaps for the most part. So whenever insertion last time and deletion today. So let's go ahead. So I'll talk about the next sort of topics. So I guess now our next sort of part in our syllabus is going to be talking about graph theory. So graph theory is something you probably went over in your CS 302 class. So I'm going to start off with some concepts that are definitely from 302, and then we'll go ahead and just do other, algorithms later on that you might not have covered in CS 302. But I have to at least cover graphs, at least the basics of graphs, before we can really go into any of those algorithms that you might not have covered in CS 302. So let's go ahead and change gears here for a little bit and talk about graph theory. So, okay. So I guess for graph theory, really, it's basically a way we can sort of think of a graph is some applications of them. Let's think of some applications of graph theory. So I guess a network can be thought of as a graph. That's kind of the best example for a graph theory. So a network. So for network, remember we have several machines, and they're also going to be connected to each other. So even for IoT, same idea. We just basically have a bunch of different machines that are connected to each other. That's really what a network really is. So a network is obvious application. So each device on the network would be a node, and then we sort of connect them with an edge. We'll go over those nodes edges in a second. I guess even a map can be thought of as a graph. So we have like a GPS on your phone. Same idea. We have different different cities, or different intersections can be thought of as a node, and we have different paths we can take at each intersection. So that could be also thought of as sort of a graph. And then, of course, we won't sort of think of examples here, but we can actually we can sort of reduce. So we can reduce problems to a graph problem. So it's something that's more for automata theory, where you can reduce problems to each other. So there's certain problems you can take a problem and you can sort of modify it a little bit so it can sort of model a graph problem, and a graph problem can actually solve this problem. That's more of reduction of problems mostly. So we might not get that far in this class. This is more of an automata theory concept. So it's sort of kind of the basic applications of a graph. So a graph, we can sort of represent a graph in the following way. So we can have it just G equals V E. That's how we can sort of describe or write out a graph. So basically V is a set of vertices or nodes, and E is a set of edges. And also we can think of it as each edge is a pair of vertices slash nodes. So I might use the word vertex or node interchangeably. They're the same idea. So an edge is really just a connection between two vertices or two nodes, just like in a network. An edge is just a connection between two machines, essentially, or yeah, so that's basically the idea. So that's sort of how we can think of our graph. So way we can actually think about it is we can sort of draw a graph. I'll draw an example graph right over here, just so we can get an idea of how a graph looks. But you've probably seen this in CS 302. So let's go ahead and sort of I'll label a graph using letters. So I'll have A, B, C, E, F. So each of these will be our nodes, like that. And we can sort of think of it as each sort of line is a connection between two nodes. So each of these lines will just be an edge. So there's an example graph. So in this graph, you want to go ahead and list this out. I'll sort of maybe briefly do this, but we can have it whereas V is going to essentially just be A, B, C, D, E, and F. In our edges, we can think of it as really just A, comma, B, A, comma, C, A, D. Let's see what else I can do here. So we have B, F. See, I think we have maybe E and F, I guess, one more. So we can keep it like this. So each of these, I should probably use parentheses, not, I think it's probably a better approach. Yeah, it's not a set, it's actually just a pair of two elements. So all of these together is going to be a set, but each of these will just be sort of an order, or a pair of two C's. On the outside, we'll have, I'll put a nice sort of bracket there. Just a little more. So that's how we can sort of think of this. This is a set of elements. So we have each sort of connection like that. Now, this example right here is going to be an undirected graph. Since the edges or these lines do not have any arrows associated with them. So for a directed graph, I'm going to go ahead and just copy this, copy all of this, and just sort of draw a version of this that's for a directed graph. Now, for the most part, we're going to be using algorithms on graphs that's going to be implying sort of undirected because it's kind of a very generic example. If we were to code any of these, then every graph would be essentially directed. So let's go ahead and do a directed graph over here. But for actual algorithms, for the most part, we're going to focus mostly on undirected, but there are moments where we're going to use actually use directed graphs. So I'll have it like this. So maybe I'll do. So here when it's directed, we have these arrows on our edge. That's how we denote that. And this is going to be a little bit different. So now for our edge count, you want to sort of have it in the correct order. So A goes to B, A goes to C, A goes to D, and then B goes to E. And actually F is going to go to B, so we're going to just swap these two. And then E goes to F, like this. So now that's sort of how we can represent a directed graph. So in this case, now the order doesn't actually matter in terms of how we list these out. We're not going to really ever list out these set of vertices and edges ever for any example. I just put that there just so that's kind of how we can represent a graph in this kind of set notation, I suppose, is the right idea. Now, if you want to have an equivalent directed graph for undirected, you'd have to sort of go ahead and sort of duplicate each edge, basically. This would give us the equivalent directed graph for the original undirected graph. If you want to have a version, if you want to have sort of an undirected graph represented by directed type of graph notation, you have to have sort of two edges like that. They go to each other just like this. So you have to have it in this type of form. So you have to actually double the set of edges. You have to have A comma B, and then also B comma A comma C, and C comma A, and so forth. If you wanted to actually represent sort of an undirected graph using a directed graph sort of notation. So if you're a coded graph, typically you actually have to do this essentially because you're coding a graph in memory. you'd have to actually maintain every connection. So you wouldn't be able to do this. So for basic, just conceptual content, we'll just sort of just use a single line with no arrows as an undirected graph. So I guess, let me see, I guess I have some time to talk some more. So a little bit I'll talk. And then also we have another examples as well. So I'll also discuss these last two. We also have connected graphs and unconnected graphs. I'll just go ahead and talk about these, and then we'll probably finish after that. So for a connected graph, basically every single node is going to, let me draw this out nicer. Every single node is connected essentially. So something like this. So whether we use direct or undirected graph, this would be a connected graph basically. Because everything is, they're all connected. So it's one graph and everything is connected to each other. Now, we could of course have it as a, so we can actually, so this graph here, everything's connected, and of course we can make it undirected or directed, it doesn't matter. The fact is that there is some sort of edge between this, so it's not disjoint like this. So for an unconnected graph would look like this. Here's how we would sort of draw this up. That would be an example of unconnected. So we have these two components right there, and they are not currently connected to each other. They're just sort of two disconnected graphs like that. So basically, that's basically how we can also have graphs. So there are examples like this. So for the most part, probably just use always a connected graph for most of our examples, but I guess this could also occur as well. So it's just if you have two different sort of networks, as I suppose. We have two separate networks that are not in the same network with each other, then I guess you can have these two separate sort of networks like that. I guess you can think of it like that for unconnected graphs. So we'll go ahead and we'll sort of go over more sort of notation with this, and then we'll go over our probably our first graph traversal as well, which is depth first search, which you've probably learned in 302, but let's go ahead and discuss that so we can go ahead and go over more. From that we can branch off and do more different type of graph problems. So I guess that's it for today. So I guess thanks for watching. Take care, stay safe, and I will see you guys on Thursday.